Any questions over anything at all before I get going?
I have one. Well, because I know you said something about like getting our exam two today.
Yes.
Will we get like feedback on our homework before the exam is due, or
Yes.
okay,
Yeah, I will get it back to you. Hopefully by Friday, but if not, definitely sometime over the weekend.
okay, okay? Thank you.
Yep, you're welcome.
So this test is just like the stuff that we've been going over so far, just on Excel.
So your homework is going to look, or excuse me, your test is going to look a lot like the last homework, plus stuff from the beginning of that chapter 7. So it's going to be doing hypothesis testing stuff from chapter 7, but you'll do it all on Excel. So I've got another data file to work with, much like what you just did on your last homework, and it'll be doing the same type of stuff that you did for your homework plus stuff that we did before the last test. So the stuff that was out of 7.1 through 7.3.
Cute.
Yep. Anything else at all?
Sent some bugs.
What's that?
Just kidding. Everybody's here now.
Oh. All right. Well, let's keep going on doing the goodness of fit tests that we started last time. We're going to do these for a few of the continuous distributions. I think I've got one for exponential and one for normal and then one for gamma. So we've got a few of the continuous distributions and talk about a couple of different ways that you can look at goodness of fit. So that'll be today. And then for Friday, I posted a video on YouTube for you to watch called, what was it? Contingency Tables. That's the stuff that we're going to talk about in section 8.2. So I'll send an email out about that as well. But that'll be the video that I want you to watch for Friday because it goes along with it's actually the same kind of concept that we're doing here for doing the chi-squared test that we have for doing these goodness of fit tests, just applied to another scenario. So this 8.1 and 8.2 are really just about the flexibility of the chi-squared test. We've already seen it for the couple of things that we've done, not only just testing for variances or variances are equal, but we saw it for doing analysis of variances to determine if a mean was different from others, or if there were row or column effects, and we've done things by categories. Now we're seeing the chi-squared popping up in, does a particular distribution fit a data set well, and so on down the line. All right, so let's look at this problem. I do have Excel, I think, up on the screen for you. It says I'm sharing it. Let's look at this problem. This is 8.1-10 out of your textbook. So they want to know if the exponential distribution is a good fit for this particular set of data, which is 90 observations looking at bad records of used computer tape. So anyway, let's talk a little bit about how you might do this. They already told you what the sample mean is, but to talk about a little bit about how you might do this and might want to try to look at an exponential distribution perhaps to see if it really does fit this well. So one of the things that you might do in this particular case is look at, say, I would do a histogram and have it graph the histogram, but for some reason I've done the histograms in Excel and it's being a pain, and I don't know why it's being such a pain for it to actually take the data that I'm giving it and say use all of the data to graph the histogram. So I'm going to do it this way instead. So I'm going to look for the minimum and the maximum values in my data set. So the minimum value is a 1. The maximum value is 238. So this one's asking us to use 10 classes of equal probability, but rather than do that, I want to use, if you were doing histograms, you would do bars that had equal width, and look how the distribution would go based on that. So let me show you what's referred to as the count ifs command. So let's say I wanted to use 10 class sizes here, just for lack of a better number to use. So I would start, let's say I start my first one at 0 and my second one at 20. Let me make these have I'm going to put a 0.5 in there just so I don't have any data point that lands in two different classes and gets counted twice. So that was why I did the 0.5. And let's copy this down until I get to the 240.5. So I just used a class with the 20. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 classes it looks like here. So I just arbitrarily picked 20, by the way. I saw that it was about 200. The difference between the minimum and the maximum was about 240, so 20 went into it evenly. It's the only reason why I did it that way. All right, so just to show you the count ifs command. So that's this one down here, the fifth one down in the list here. So I'm going to use this to use multiple criteria to on an array, on a set of data. I use this command for multiple criteria that the data need to satisfy. The count if command without the letter S only lets you use one criteria. So the count ifs lets you put in multiple criteria. And this is helpful if you want to count things in between 2 points. So my criteria range is this one. I want to make it an absolute reference because I want to be able to copy and paste this particular command down to the next columns. So the criteria I want is that it's between the 0.5 and the 20.5 for my first class. So I want greater than A14. So remember to get that notation in there for Excel to understand that you want the greater than sign, actually use that as an operator. So we put the quotations around the greater than and then use an ampersand to go back to refer to the cell reference. But I also want to make sure that it's less than the right boundary. So again, my criteria will be, or excuse me, my range will be this data set, make it an absolute cell reference again. And then criteria 2 is that I want it to be less than the A15 cell. And then if you wanted more criteria the data needed to meet, you could put those in. But in this case, I really just wanted in between those two values. So I did greater than A14, less than A15. If you needed a greater than or equal to or a less than or equal to in here, you would just put the equal sign behind the greater than or the less than sign. So you would have greater than equal to there or less than equal to there. In this case, it doesn't matter because I specifically picked values that weren't in my data set, so I don't need to worry about the equality part. All right, so there's 30. And then if I copy this down, I see that I could do a chart, but really I just wanted to see that as I went down with my classes, my number of entries went down as well. So remember, your exponential distribution looks like an exponential decay type of function, right? It starts up at the y-axis and then drops. It decreases from there. So that's what I wanted to see from my distribution if I really did see that kind of thing. If you really wanted to see a histogram, let's see if it actually works on that set of data. Nope, sure didn't. Let's try a bar chart instead, because it likes to be a pain. There you go. If I did a bar chart instead, you can kind of see that it does drop down like that and flattens out at the bottom. So the only reason, again, that I did this is that in general, if you're working with data, you're not going to be told, oh, by the way, fit this to an exponential distribution. You're trying to take the data and see what type of distribution might be best used to model it. Well, then you need techniques to be able to do those kinds of things. So this would be one way to do that. break it up into classes, and then see what the distribution looks like from those classes. And so in this case, I just did a bar chart and dropped it down. All right. That was not necessarily anything here or there about how to do this particular problem. I was just telling you why you might want to do such a thing with working with a real data set on trying to determine what distribution you might want to use. I looked numerically, I looked graphically at what the distribution looked like and said, hey, that might, you know what, an exponential might do a good job of modeling this. Another reason why I might want to use an exponential in this kind of a model is if you've got something dropping like this and you know it's also a continuous distribution, you might want to make sure that you use an exponential rather than, say, a Poisson. All right, so let's actually do what the problem tells us to do. The problem says to use 90 observations and 10 classes of equal probability. It also tells us what mean to use, but if you weren't given the mean... Oh, hi, Ashlyn, yes. Ashlyn, did you have a question? Two participants raised their hand. All right. I can't hear you. I don't hear Ashlyn. Are you talking, Ashlyn? Chat. I don't think you can hear us. I don't think you can hear us. You can't hear us. This is true. I agree with you. Can you hear me? Well, of course you can. No. Okay. My speakers got muted. Now I think I can hear you.
Oh, that's fantastic.
Ah.
That helps. That helps so much.
It does help when I can hear. All right.
Okay. I am one of those people that had questions.
Okay. Well, good. I'm glad.
I was sitting there talking, and I was like, man, I don't think he can hear me.
Nope, I couldn't. Sorry, I have no idea when my speaker got muted. It was on before I started. Yeah, go ahead. Sorry.
Okay, so we're breaking it up into classes to try to show that we can make it exponential.
We are the only reason why I was breaking it up into classes here was to see whether or not it even made sense to do an exponential. If I saw something that I broke it into classes and I saw something that increased and then decreased, an exponential wouldn't make any sense because an exponential doesn't increase at all. It always drops.
Yeah.
So that wouldn't make any sense. So that's the only reason why I was doing it. It's, again, like I was saying, when you're doing problems, quote unquote, in the real world, you're not going to be told what distribution to use. You're going to have to come up with ways to try to figure out what distribution might be the best one to use in order to model a particular situation. So one way to do that is to do some numeric counts by classes or get a graph by classes to see, is it kind of a bell-shaped curve? Would a normal distribution work? Does it go up but then down really quickly? And so a different type of distribution would work, like there's other ones called Pareto and Weibull and those kinds of things. In this case, it really did look like it was dropping, so an exponential probably wouldn't be a bad idea to try first.
So then why didn't you do 0.5 in the values? You just did 20.5.
No, I did the 0.5. It's just that it's the lower class value. I need one more value to be able to define my classes than I actually have classes, because I need that left-hand endpoint. Oh. So I used it in defining my classes.
Okay.
That's why.
Okay. Yeah, I think I'm back.
Okay. Other questions?
Is this being recorded?
Yes.
Better now. You're frozen.
We okay?
It's just my...
I haven't moved anything.
Oh, you haven't moved?
Yeah, I haven't moved, so...
Oh, that worried me out. I thought it was...
Now I'm moving the mouse. I was just making sure no one else had questions before I went on and actually did the problem.
Technology's scary.
Yeah, I agree. It's very... Well, mine just randomly shut off my speaker, apparently. I don't know why. Anyway. All right. Back to what we were talking about now. Okay, so we want to try to model this to an exponential distribution. The problem asks you to use 10 classes of equal probability. All right, and then use this as our... pardon me. This is our estimate for theta. Now, of course, if the problem didn't give us the 42.2, we could just use the data to get us our estimate. So if I take the average of the data here, I get exactly 42.2. But again, in quote-unquote real-life situations, you're not going to be given what estimates you should be using for the different values. So anyway, all right. So let's see how we do this. So I'm going to use this 42.2 to use as a mean for our exponential distribution. So I need to figure out endpoints of classes so that I have basically a 10% chance of landing in each of those classes. So what I mean by that is, let's see here. If I go over, maybe, hit new share. Let's go over to, I'm going to try Zoom's whiteboard here real quick. So when you have your exponential distribution, it looks like so, right? I want to divide this up into pieces where I have a 10% chance of falling in that range, a 10% chance of falling in that range, a 10% chance of falling in that range, and so on down the line. And I'm purposefully making those bigger and wider because, of course, the more that the exponential distribution drops, the less probability there is under it. So if I'm going to make equal probability, those values should get farther and farther apart. So to be able to figure this out for a particular value, say for your 0.1, I would need, if this is my x value here, I would need 1 minus e to the negative x over theta to equal 0.1, right? To be able to figure out what that x is. So if you solve this for x now, you would have, I'm going to write, I know it's going to be goofy, but I'm going to write it as 1 minus 0.1. And then I need to take the log of it, will be negative x over theta. Right? I would subtract the 0.1 over, add the e to the negative x over theta to the right, take the log, and then I'll need to multiply by negative theta to solve for x. Now the reason why I left this as a 0.1 is because if I wanted this at 0.2, I would use a 0.2 here. If I wanted it at 0.3, I would use a 0.3 here. I'm leaving this general because I need to use this in Excel here in a second. For the other distributions, we have the, like distribution.inv command. We don't have that for the exponential distribution, which is why I had to solve it using the cumulative distribution function here. All right, so let's go back over to Excel. All right, so for your first, your lower left-hand limit will be a 0 for your exponential distribution because you can't get any lower than 0. This one needs to be negative theta, which was the 42.2, times, oops, let me do it this way. Sorry. I'm going to make these...
Dr. Joe?
Yes.
We can't see the Excel file.
Well, of course you can't.
Now we can. Thank you.
Yep. Sorry. It's like, of course you can't, because I only hit new share. Apparently it ignored me. Hold on just a second. I got an email about... I don't know what that means. Okay. I got an email that floated in saying something about read immediately about Zoom, and I thought there was going to be an issue, but there wasn't. So anyway, sorry. All right, so I need these endpoints that correspond to the probabilities of 0.1, 0.2, and so on up the line. So I need negative theta, which was the 42.2. And I need to multiply that by the log of 1 minus the probability here. I do need to go back to this D11 and make it an absolute cell reference, because I don't want it to change as I copy down. This is why I left that when I was doing that on the whiteboard, and why I left that as a 0.1, because I wanted this general, because I needed to solve this equation, because I need to find those boundaries for each of those probabilities. So I'll take this and copy it down to here. I know that this lower limit's going to be 0. This upper limit is just going to be infinity, because that's where my support goes off to infinity there. All right, so I want to count what's in each of these classes. So we'll do that count ifs command again. My range is the range of data. Absolute cell reference that. I want it to be greater than 0. Whoops. I forgot to put the ampersand in there. That's why it went off on me. Greater than 0, and for that range, I want it to be less than the one that's right next door. Oops. Okay. This should be 14 up here. There we go. I'll go back into the cell so you can actually read it. There we go. So I want this to be greater than the 0, so I want it greater than E14. I want it to be less than this this right-hand boundary that tops off the first 10%. So this would be your 10th percentile, if you will, the 4.446. All right, I'm going to copy this down. And then the last one that I want is, what is it? It is, I want to be, I just want the count if part. I can use count ifs again, but I just want if this is greater than that left boundary. So greater than the 96, 7.169. I don't have an upper bound on that last one because it goes off to infinity. So this one is just less than, I didn't really need to say it was greater than 0 because it's exponential, these better be greater than 0. And then just copy this down. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. Cool. Good. Everybody okay with how I got those?
So the column E is those are your X values?
Those are the X values from the exponential distribution. So this would be the theoretical distribution of where you cut off the 10th percentile, the 20th percentile, the 30th percentile, and so on.
Okay, so then what is in column F? Is that how many are in each of those?
So yeah, so this 8 represents how many are between 0 and 4.44. The 10 is between 4.44 and 9.4, and so on down the line.
Okay, thank you.
Yep. All right. Oops. My screen sharing is paused.
Dr. Joe, the
Yes.
first one you did in column F, what is that in between? That's in between the 4.4 and which other value?
This 8. The 8 is it's the one above it. So the 8's between 0 and 4.44. The 10 is between the 4.44 and the 9.41, and so on. Okay. All right. So since we're using classes of equal probability, the probability that you're between 0 and 4.44 is 0.1. The probability that you're between 4.44 and 9.4 is also 0.1, and so on down the line, if this is an exponential distribution. Since there are 90 possibilities here, the expected number here would be 9 for each of these, because I would just do the 90 times the 0.1. So these are your observeds, and these are your expecteds. And since we're using classes with equal probability, the expected is going to be 9 here. Does that make sense for each of those? And since we're using equal probability, the expected value should be equal for all of those?
Yes.
Yeah. Okay, cool. All right. So then we'll do the same thing that we did yesterday. We'll do yesterday, Monday, whatever day it is. I can't possibly keep track of days when I don't leave the house. So we do our observed minus expected squared divided by expected. And
Joe,
yes.
out of the Zoom, so I didn't get an explanation on the expected. I see a lot of 9s.
Oh, okay. So the 9. So remember, these classes were made from equal probabilities. So since there's 90 data points and probability is a 0.1 for each of them, the expected value that's in any particular class is 9. Because all the probabilities are the same. That's why there's 9s. All right. Yep, you're welcome. So we'll copy that down for our observed minus expected squared over expected. So our test statistic, again, will be adding all these up. And we want to compare to that to our critical value. Remember that our critical value is based on the chi-squared distribution. The problem asks us to use an alpha of 0.05. And now we need degrees of freedom. Okay, so in this particular case, we have 10 classes. We lose 1 degree of freedom because remember that once we've determined k minus 1 classes, the kth one's already determined for us. So we lose 1 degree of freedom just by the fact that we have the last class is always determined for us. So that takes us to 9. And then every single parameter that you have to estimate using the data, you lose another degree of freedom. So in this particular problem, we're estimating 1 parameter, the theta, by using the mean. So that takes our degrees of freedom down to 8. So when we're doing our chi-squared distribution here, we'll have 8 degrees of freedom from the 10 classes. Again, we lose 1 for just the fact that the last class is completely determined for us by the rest of the classes, and then we lose another 1 for estimating a parameter. So in this case, sorry, there you go.
Can you click on the TS value again?
Yep, it's the sum of this last column here.
Okay, thank you.
Yep, you're welcome.
Could you explain why we did the right tail again for the chi-squared?
Because the farther away this gets from the actual expecteds, is the farther away the observers get from the expecteds, the more error you get in a positive direction. So it's always going to be above the value as opposed to below it because we're squaring. We're doing all the squares of the errors. So it always makes it bigger.
Oh, okay.
Yep.
Is that when we looked at if that was too large on top?
Yep, that's right. If it's too large. Yep, that's right. If we want to see a measure of how good this particular distribution does at modeling the data, that's when we would do our p-value. So we'll do our chi-squared distribution right tail for that test statistic based on 8 degrees of freedom. We got a p-value of 0.94. So this is a really, really good model based on this particular data set. This would be a really, really good model for modeling this situation. Questions on that?
So you want your p-value to be closest to 1?
The bigger the p-value is, the better the model is.
Okay.
And honestly, when you're doing quote-unquote real-world data, the chances that you're going to get this 0.94 p-value is probably pretty small. But, if you get the 0.5, 0.6, that's pretty good. I mean, you're using it to model anyway. There's always going to be some uncertainty in modeling, but in this case, for this particular one, this p-value being really good really does give a good model for it. So the bigger the p-value, the better the model for us. All right, let's see if we can do another one. Oops, I didn't copy the problem down. Well, shoot. Sorry. I give you the directions for the problem. So this is 8.1-11 as indicated by the bottom. I can't believe I did that. Let me see if I have it already copied. I thought I did all of those. Give me a second here. Maybe. There it goes. All right, so like I thought I made a copy of that already. Okay, so there are the measurements. I'm on the wrong page. I don't know why I don't have the directions saved in there. Sorry. All right, so the first thing this asks you to do is it wants you to group the data into 9 classes of equal width. Starting with the class 2.125 to 2.145. All right. So to do that, in our case, I'll start by putting in these first 2 class widths, or excuse me, those 2 class boundaries, and copy this down. So that should give me 9 classes. If I check, that's the right endpoint for the first class. So 2, 3, 4, 5, 6, 7, 8, 9. Good. Okay. So it wants us to group the data into these boundaries. So we're going to use that countifs command again. Use that range, and then be greater than the lower value and less than the upper value. So that's the same command that I used in the previous one to count the classes. And then let's just copy that down. All right. So they told you what class width to use and how many classes to use, but the way you might have come up with these would be to do what I did the last time. Find the minimum value, which I think is 2.13 if we look around. Maybe, I don't know. You can always find it. Find the maximum value. Pick a class, how many classes you want. Use that for your class width and do these counts. This is what we did in on the stuff with the exponential distribution. Notice again, this is what I was mentioning in the last problem. I would not want to use an exponential distribution to model this because it goes up and then it goes back down again, right? In fact, if I do a bar chart here, I kind of see it goes up and back down again, and our classical one for going back up and back down again is the normal distribution, right? So this is what's telling me that, hey, maybe I want to try to use a normal distribution to model this particular data. Again, this is just a quick check on, I'm looking at the shape of the distribution based on these classes and saying, hey, I recognize a distribution that kind of looks like this. I'm going to try that and see if I can model it that way. All right. So if I'm going to use a normal distribution, what I need to do is I need to figure out a normal distribution to use for this data and then figure out the expected number that fall in between these values. So this would be your observed column here. I still need an expected column. Now, in the previous example, we did probabilities of were the same and found the classes. Now in this case, the probabilities aren't the same because we fixed the class width. Based on the class, the probability is going to change. So to figure out our expecteds, we need to use our normal distribution. So the first thing I need to do is figure out what our sample mean is. Let's write mean. And then our variance here. So if I do the mean here, of the data, and then do the variance of the data. I don't have that information given to me in the problem, so I have to use the sample to be able to approximate the mean and the variance. All right. So if I want to know the expected number here, I need to calculate the probability that a value, a normal distribution value, is in these ranges, and then multiply it by the number of things in the sample. So in this case, the number of things in your sample was 100. So I'm going to add an extra column in here just so that I can show you what the probabilities are. So in this case, I want to use the normal distribution. The x value I'm going to use is the 2.145. The mean that I'm going to use is the 2.2015. The standard deviation, of course, is the square root of the variance that I found here. And then I want cumulative. So what I'm computing here in this first cell is the probability that a value from the normal distribution with the mean of 2.2015 and whatever the standard deviation is, the probability is less than that 2.145. I'm not going to use the in-between. I'm going to use the whole less than, because when I do the normal distribution, it's continuous. It goes off to negative infinity. I don't want to artificially cut it off at that 2.125 piece. All right. So this tells me the probability that a particular value is less than 2.145 from that normal distribution is 0.01. If I want the expected number, I would take 100 times that probability. Okay, so this is the expected number that should fall into this class. For the other ones, I need to do a similar thing. So I want less than, I should have just done the standard deviation here. I want less than the 2.1665, but I need to subtract off the probability that I'm less than the 2.145. I need the classes, so let me change this to a 13. All right, so again, just to explain what I'm talking about here, this first part in the formula is the probability that a value is less than the 2.165. This second part is the probability that we're less than the 2.145, so I'm subtracting the two to get what's in between. And then I'll copy this down to here. Why did oh, I know why. Because guess what I forgot to do? I forgot to make these absolute cell references. So let me do that. All right. Make these absolute cell references. And then the last one, I can just do 1 minus the sum of all the other probabilities, because these all have to add up to 1. So this last one, I can just do 1 minus the sum of the other ones that I did. So again, the only reason why I put this in here is so that you could see the probabilities that we're computing for being in between these classes. It's the only reason why I put it in there. You don't have to put this part in here. I could have put the 100 times the whole thing and just put it all in one cell. I just wanted you to see these probabilities here. Now I should be able to just copy these down to get our expected values. Any questions on where I got those from?
Do you mind showing the probabilities formula? My screen like went out when you like showed like the absolute like reference and changed that.
Oh, this one here? Is that what you needed?
Yeah, like all of that. Like I heard you talking but didn't see it.
Okay, sure. So this formula, this first part is computing the probability that it's less than the 2.165. And then I want to subtract off the remainder of it because I want it in between those two values. So the second part is subtracting off the probability that is less than the 2.145. So that's where that formula came from.
Thank you.
Oh, you're welcome. Other questions?
So your probability is column is the probability that you would observe something within that class.
Yes, the probability that using a normal distribution based on these parameters, I would observe a value that's in that class. Correct.
Okay. So then we estimated the two parameters there, the mean and the variance.
Correct. Yep, we estimated both of them. That's correct. All right. Well, the rest of this now is the same stuff we've been doing. Observed minus expected squared divided by expected. And drag it down. Our test statistic is going to be the sum of those. And our critical value then, of course, is based on your chi-squared distribution. Using an alpha of 0.05, now we need to worry about our degrees of freedom. Okay, we started with 9 classes. When we start with 9 classes, we lose a degree of freedom because of the fact that the last class is determined for us. So that takes us to 8. And now in this scenario, we have estimated 2 parameters. So we lose 2 more degrees of freedom. So the degrees of freedom in this case is going to be 6. It was 9 classes. We lose 1 just off the top regardless because the last class is determined for us. And then we lose 1 for each parameter that we're estimating. And we estimated 2 parameters here. All right. So we didn't reject. And we could check our p-value here as well. So this on 6 degrees of freedom. We didn't reject, but that p-value is not so hot, right? So let's look at maybe a reason why our p-value is not so hot. In particular, let's look at this last entry. That last entry is big relative to the other entries we have. And notice why it's big. It's big because this expected value, remember when we do, when we calculate our statistic, the expected value goes in the denominator. We're putting an expected value that's very small in the denominator. When we do that, that piece really isn't estimating a chi-squared random variable very well. Remember that this works out well if your expected values are not making the fractions turn out to be big. The book says that it works. Usually you worry about the expected value to be about 5. That's a really good fit. But the book says it even works when the expected value is about 1. The expected value is not about 1 here. This is 0.1. So this is really skewing the data. So what we would want to do instead is group these last 2 classes together and see what happens. So let's do that in this case. So let's group, and actually the directions in the problem actually say group the last 2 together. So if we group the last 2 together, this would be a 2. I can count that myself, right? This probability needs to change to 1 minus the sum of the previous probabilities. It's the last class. Okay, so then I've got observed minus expected here. That would be the last class. Let me delete this out and everything should get fixed. Last thing I need to worry about though is the degrees of freedom because I deleted a class, so I need to change this to 5 rather than 6. And change this to 5 rather than 6. And notice our p-value went up significantly. And again, the whole reason why we did that was because that last set of probabilities, excuse me, not last set, that last probability was really, really small. Not the probability, the expected was really, really small. When it was really, really small, it was unduly influencing that last piece in the statistic, which was throwing off whether or not this was a decent fit or not. The book also suggests pooling the bottom two together and see what happens. If you notice that this difference is pretty big, which is why we've got this difference here is fairly large. But if I make these two to get together, then this is probably not going to be quite as large, and you'll probably get even a better fit. So the actual directions in the book said group the last two classes and group the first two classes together and see what happens. But I think I'll leave it there just so that you can see that we really did improve the p-value by putting those two particular classes together. Not fantastic, but it was better than it was. Questions on that at all?
So when you talk about like improving the p-value, like making it a greater value, because I guess I'm a little confused because like the p-value is supposed to be that our sample is not, or at least that bad.
Yes.
So how is the higher p-value related to it being at least that bad?
So, yeah, I understand what you're saying. So if the p-value is the probability that you reject when you shouldn't, right? So the p-value being about 0.4 would say that, okay, well, based on this sample, if I took another sample, because based on this sample, I wouldn't reject. If I took another sample, what would be the probability I would land at least this bad for the sample? So the probability is that at least this bad, it would still be a 0.141% chance. So I could still have the let's see, I'm saying that incorrectly. Let me try that again. So your p-value is your probability that you actually would be above that test statistic in this case. So related to this particular problem, if you took another sample based on the fact that you think this is a normal distribution, what would be the probability that you got this value or a higher one? So related to the fact that this is an okay distribution, meaning that this isn't that much of an outlier based on the fact that we were using the normal distribution. The fact that you could get something this quote-unquote bad or worse has a fairly decent shot of happening. So the fact that you're using the normal distribution to generate this data isn't necessarily a bad assumption to make. That's the idea. That this really isn't a bad sample based on the fact that we are assuming there's an underlying normal distribution associated with it. Does that make sense?
A little bit.
A little bit. Let's see if I can explain it in a different way. So, in general, say if you just had a regular old doing a test of one mean, and you think the mean is 50, and you had a sample that was a mean of 55. If the p-value for that mean of 55 is 0.3, then there's no real reason to say that you would think that the mean's different from 50, because there's still a 30% chance that you could have got a 55 or something worse. So there's not any evidence to say, hey, the mean's not really 50. because I had a 30% shot of getting something at least this bad anyway. So in this particular case, if I had the underlying normal distribution, the chances that I would get this bad of a sample being this far from the normal distribution or worse, I have a 40% shot of getting that bad of a sample, which honestly is a pretty decent shot of getting that quote unquote bad of a sample. That's what I'm trying to say. Did I say it any better that time?
Yeah, the numbers help.
Okay, cool, good. Any other questions at all? All right, I will record a video later with doing this one as an example, the 8.1-14. I'm not going to give you any assignment on this stuff yet. I'm going to wait till next week after we get through section 8.2 as well, because you have your test to work on this week. So I will get this last example done, post that to YouTube either this afternoon or tomorrow. I'm not in any huge hurry since, like I said, I'm not going to give you an assignment on that yet until after you do your test. So, all right. Anyway, if that's everything, I guess I will talk to you all later.
Thank you.
Yep. Thanks. See y'all later.
Someone asked a question in the chat.